All right, everybody. Now we're getting to the good stuff, right? We've looked at the overview of the solar system. We've noticed that, yeah, the solar system has all of these properties, and now we're trying to come up with the best theory that we can to explain the solar system as we see it, the solar system that we live in. So, what types of materials can be a liquid or a solid near the orbit of Mercury in the early solar system, right? In the early solar system, if you are living, or not living, I mean, no one was living there, but if the material in the protoplanetary disk that was at the distance that Mercury is to the sun, what could be solid or liquid? First off, I want to be a little clear about how do you read this axis, right? The vertical axis here is pretty easy, right? The vertical axis is linear, right? It just goes 0, 500, 1,000, 1,500, etc., right? This axis is what you call logarithmic. Basically, they're taking this big span of numbers from 0.01 all the way to 100, and they're squishing it down so that it is easier to read, so that you can get a little more detail. And how do you pack all these numbers into the graph here? You do it by changing the scale of the numbers, right? Every time you go up a power of 10, you change the scale. So you'd read it like this, right? It goes 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, to 1. But then once you get to 1, then it becomes 2, 3, 4, 5, to 10. And then once you get to 10, it becomes 20, 30, 40, 50, all the way to 100. So if you want to know how hot the disk was, how hot the protoplanetary disk was at 0.4 AU, then you go to 0.1, you go to that, approximately that number, 0.1, 0.2, 0.3, 0.4. Okay, so we're looking right here. And it looks to be about 400 degrees, right? So, at 0.4 AU from the sun, well, it wasn't the sun yet, right? It was still the protostar, but in the early solar system, that location at the disk was about 400 Kelvin. What can be a solid or a liquid? We're just going to ignore the Fahrenheit scale here because this is science. We're not using Fahrenheit. Let's see here. Right? Water freezes at 273. Water boils in space, which is, of course, that's where this was in space, right? The water boils at 150. Rock vaporizes at 900, and metal vaporizes at 1,000. So what can be solid in the disk at 400 Kelvin? Just this stuff. Just the rock and the metal, right? Water boils away, so it can't freeze or be a liquid. And so, what types of materials can be a liquid or a solid at 400 Kelvin? Just the rock and metal. Right, at 400 Kelvin. Right? What type of material can be liquid or a solid near the Earth? Well, how far is the Earth from the Sun? 1 AU, right? So at 1 AU, this looks like 300 Kelvin. So at 300 Kelvin, what could be solid or liquid at those temperatures? Well, the rock and the metal. Here on Earth, well, near the Earth. Out in space, here on Earth, what I was going to say was, here on Earth at 300 Kelvin, water can be a liquid. Water can be a liquid on Earth. But the Earth hadn't formed yet. This was the early solar system. The Earth hadn't started forming yet. There was no Earth, there was no atmospheric pressure to let water be a liquid, right? Back when everything in the solar system was just the sun and the protoplanetary disk, any water out there in space, that still boils at 150. Right? Water can be a liquid at 300 Kelvin here on Earth at sea level. But out in space, no. Water out in space at 300 Kelvin still vaporizes. So even at 1 AU, the only thing that can be solid is rock and metal. Which, surprise, surprise, what is Mercury made out of? Rock and metal. What's the Earth made out of? Mostly rock and metal. What can be solid at the orbit of Jupiter? Well, Jupiter is 5 AU from the Sun. So where's 5 AU? 1, 2, 3, 4, 5. Right there looks like... I mean, what a surprise. Turns out that at 5 AU, the temperature is about 150 Kelvin. Or just a little less than 150 Kelvin. So, what can be a solid at 150 Kelvin? The rock and the metal, but also the ice. Right? If the ice boils, if the water boils at 150, then, bring that down to less than 150. What can be a solid at 5 AU from the sun? The rock, the metal, and the ice. This is why we think, in order to form a gas giant, in order to form a Jovian planet, you've got to have that icy, rocky core. You've got to have a protoplanet made of rock and metal and ice. And once you make that protoplanet out of a lot of ice, then that protoplanet has enough gravity to accrete the gas out of the disk. The gas is not a liquid or a solid, right? The only thing that's solid is the rock, metal, and ice. The gas still stays gas. Which planets formed where only rock and metal could be solid or liquid? Well, the terrestrial planets, right? The terrestrial planets, you could list them if you want, but the terrestrial planets, Mercury, Venus, Earth, and Mars, they formed inside the frost line where it was too hot for ice, so the only thing that can be solid is rock and metal. Which planets formed where rock, metal, water, and gas could be liquid or solid? That's the Jovian planets. Now, doesn't that contradict what I just said when I said, out past the frost line, I said the gas is still gas? What do we mean when we say that the gas could be a liquid or a solid? Well, we'll get into this a little later, but under plenty of pressure, once that icy, rocky core, right? Once the Jovian planet forms that protoplanet out of rock, metal, and ice, then that protoplanet can start gathering gas out of the disk. It'll pile all that gas up onto its surface, and you'll start accreting that big Jovian atmosphere. And hey, once you have a whole bunch of gas piled up in the atmosphere of that planet, then the pressure on all that gas can liquefy it. So actually, the gas in a Jovian planet, the atmosphere in a Jovian planet, a lot of that gas actually is under such high pressure that it liquefies. And so, yes, at the end, right, once you finally build the Jovian planet, the gas can, most of the gas can be liquefied. But it wasn't like that originally. right? Originally, before the protoplanet formed, the only thing that could be formed the only thing that could solidify and condense and accrete out past the frost line is the rock, metal, and ice. Okay, so if we start putting these pieces together, and then we say, all right, here are all the assumptions that go into the solar nebula condensation model, and you say, okay, based on these assumptions, predict the composition of the leftover small bodies in the inner solar system, right? After you condensed a whole bunch of solids, and then those solids accreted together. And when I say solids, I mean what condensed out of the disk? The dust and the ice. And then the dust and the ice accreted together to form these small bodies, chunks of rock and ice. Well, if you're in the inner solar system, it's hot, it's warm. What material can be solid to form the planetesimals in the inner solar system? Just the rock and metal. What can the leftover planetesimals in the outer system be made of? In the outer solar system be made out of? Well, in the outer solar system, it's cold, it's out past the frost line. You can form those planetesimals out of rock, metal, and ices. Water ice mostly, but also carbon dioxide ice, ammonia ice, right? We're sort of using water here as a proxy for all of those hydrogen compounds. So there you go. What are the leftover planetesimals in the inner solar system? Those are the asteroids, right? So what are asteroids made out of? Mostly rock and metal. The leftover planetesimals in the outer solar system are the comets. What are comets made out of? Rock and metal and ice. Mostly ice, though, right? Because there's a lot more water in the solar system than there is rock and metal. And so if you're forming a planetesimal out of rock and ice, it's going to be mostly ice. So the comets are mostly ice with a lot of rock and metal mixed in there. All right. Let's test our assumptions here, right? We've got this solar condensation model, or I usually call it the solar nebula theory, right? This model that explains how the solar system formed out of the nebula. But let's test this, right? All of these are conclusions that you would logically come to based on the model for how the solar system formed. But let's test whether these conclusions actually are backed up by the properties that we see in our solar system. All right. The conclusion from the model is that the solar system formed from a single cloud rotating in a single direction, right? So that blob of gas that clumped up out of the nebula, and then it was spinning counterclockwise, and therefore everything that formed out of that single cloud was moving counterclockwise, and therefore all of the planets should rotate and revolve counterclockwise. Do all of the planets revolve around the sun counterclockwise? Yes, they do. Do all of the planets rotate counterclockwise? No. Remember what the two exceptions are, right? The two planets that don't rotate counterclockwise are Venus and Uranus. So there's a couple of exceptions there. Most of the solar system, right? Well, all of the planets orbit counterclockwise. Most of the planets rotate counterclockwise. So gosh, it sure seems like, that conclusion seems reasonable, but there are a couple of exceptions. So, not entirely supported by observations. You would conclude that the solar nebula had much more hydrogen and helium than rock and metal, therefore the largest planets should be the ones made out of hydrogen and helium, the Jovians. Is that supported by evidence? Sure, right? The largest planets are the Jovians. The terrestrial planets are made of rock and metal, and there's not that much rock and metal in the nebula, therefore the rocky planets are small, which they are. The temperature was too high close to the sun for Jovians to form, so none should be found there. You shouldn't find any Jovians near the sun, only far from the sun, out past the frost line. Is that supported by evidence? Yes. The solar wind should clear out the space between the planets. Yeah, pretty much. You know, there is... Well, there are the leftovers, right? The space between the planets wasn't completely cleared out. There are still asteroids and comets in between the planets. So I suppose that's not entirely supported by evidence. The solar wind, right? The solar wind is a wind. It's a breeze blowing away from the sun. The solar wind was strong enough to clear out the gas from between the planets, but not the heavier stuff, not the leftover planetesimals. No solid bodies should be formed beyond the Jovians. Is that true? Are there no solids beyond the Jovian planets? No, sure there are. Right? Pluto, Charon, Eris, all the Kuiper Belt objects, and then also the comets, right? The Kuiper Belt objects and the comets are out there beyond the orbit of Neptune. They're out there beyond the Jovians. The solar nebula was originally a sphere, so the planets should revolve at random angles, not in a plane, right? If the nebula started out as a sort of roughly spherical blob, then the planets that form should go in random angles, right? One planet will go like this, another planet will go like that, another planet will go like that. Is that true? Is that what our planets in our solar system are doing? No, right? The planets in our solar system all orbit in the same disk, in the same plane. Huh. Well, it sure seems like this solar condensation model isn't completely backed up by all the evidence. What's going on here? Well, it turns out that this model isn't complete, right? This nebular condensation model answers some of the questions, but not all of them. So clearly this model is not complete. We need to add some more bells and whistles. We need to add some more details to this model to hopefully make it more complete, more powerful in explaining the properties in our solar system. So if we throw in collisions, if we allow for objects to be colliding, what effect does that have on our solar system? Well, the collisions between particles cancel out their up and down motions, leaving them revolving in a thin disk around the sun, right? Originally, the cloud that made our solar system was roughly spherical, and things were moving in random directions, right? Some particles were moving north, while other particles were moving south. And so the particles moving south and the particles moving north crash into each other. And their momentums cancel out, right? One moving south, one moving north, they crash into each other, and they stop moving north and south, and they just keep on going counterclockwise like they already were. That's how the cloud flattened into a disk. After all these collisions happened, all the up and down motion canceled out, and so that blob flattened into a disk where everything kept on moving counterclockwise, but not north or south anymore. Once you allow for the collisions of particles to cancel their vertical motion, their up and down motion, the only motion that's left is the rotational or the revolution motion, the counterclockwise motion. Is that supported by evidence? Yes. Right? That's why our solar system is a disk and not a sphere. The planets experience large collisions which would have their rotation directions changed. Sure, that can happen, right? The best explanations that we have for Venus and Uranus, right? Venus and Uranus probably formed rotating counterclockwise just like the other planets, but then some big protoplanet smashed into them, right? If you know what, what can I use here? Let's see. Okay. I'll do something silly here, right? So, the planet was spinning counterclockwise, right? So, Venus and Uranus probably formed rotating counterclockwise just like the other planets, but then some big protoplanet comes in, collides with the planet, and gives it such a kick that it kicks the planet and starts it spinning backwards. Right? That's probably what happened with Venus, right? Venus was probably rotating counterclockwise just like Earth, and then Venus had the bad luck of getting smacked by a giant asteroid or a big protoplanet, and it knocked it backwards and got it spinning clockwise, which is why that's why it's rotating clockwise today. Uranus was probably similar, right? Back there in the early solar system, there was a lot of leftover planetesimals crashing into everything. It is entirely likely that Uranus also was formed rotating counterclockwise, right? Rotating counterclockwise, and then something big hit it and smacked it on its side so that it started spinning sideways. So yeah, right? It is, you can't explain why Uranus and Venus are rotating not counterclockwise with just the condensation model. The condensation model would say, no, everything should be moving counterclockwise. And most things are. So that model is mostly correct. But if you add in the possibility of collisions, that Venus and Uranus just had the bad luck of getting hit by a really big collision that changed its rotation, and that's why those two aren't going counterclockwise like the rest are. Now once you have a condensation model with collisions, now we can explain the motion of all the planets, and not just most of them. Objects in the far outer solar system orbited so slowly that they would have experienced few collisions, leaving small solid bodies behind. What are we talking about here? We're talking about the Kuiper Belt, right? The far outer solar system, out beyond the orbit of Neptune, the Kuiper Belt, where there's billions of comets, little comets orbiting out there at the edge of the solar system, and the tiny little Kuiper Belt objects like Pluto, right? Out there at the edge of the solar system, those objects are orbiting the sun so far out there that they move really slowly. They're really far apart. And if all these comets are small and they're moving slow and they're really far apart, then they're not going to collide very often. And if they're not going to collide very often, then they can't accrete together to form anything bigger. Why are the planets so big and Pluto is so small? Well, the planets formed closer to the sun, where everything was moving faster and things could collide more frequently, and out of those collisions you could accrete bigger planets. Way out there at the edge of the solar system, those comets and Kuiper Belt objects move so slowly, and there's so much space out there. They're so far apart that they just don't collide very often. They still do collide. There are still collisions out there, just not as often. And therefore, they couldn't accrete together to form big things. So all they could form was small things. Small things like Pluto, small things like comets. All we find out there, beyond the Jovian planets, the only things, once you sort of take the rate of collisions into consideration, then this model would predict that, sure, way out there at the far outer solar system, the only thing that you could have are small things, small bodies. So this is a way to explain more of the exceptions, right? That the condensation model by itself doesn't explain everything. But if you add more bells and whistles, if you add some more detail to the model, then you can explain the exceptions, and now you can explain pretty much everything, and not just most things. Right? That's why we say that the solar nebula theory is the best theory that we have today. It's not the only one, right? We've had lots of theories over the decades, centuries, right? There have been lots of ideas for how our solar system formed. This is the best one that we have right now. What makes it the best one? The fact that it can explain most, if not everything, that we see in the solar system. Right? The strength of a theory comes from the amount of evidence that it has backing it up, and just the condensation model by itself explains most of the solar system, but not everything. But if you improve this theory by adding more detail, adding more nuance, adding more explanations for how things work, then you can make it a better theory by having more evidence to back it up. Right? So that's why I say the solar nebula theory is the best theory that we have today to explain how solar systems and planets form. If we find a better idea, if we come up with a better idea that has even more evidence to back it up, then it would be an even better theory. And we'll see if we can't do that. Because right now, the solar nebula theory is the best theory that we have for explaining our solar system. And now the question is, hey, we've found a lot of planetary systems. We've found thousands of planets orbiting around other stars. Does this theory explain those planets also? Yes or no? Right? Does this theory work great for all planets? Or is there a better theory out there yet to be discovered? That's what we'll be getting into over the next few weeks. So, like I say, we're getting off to the races, right? We've got this great theory. We've got this great theory for how our solar system formed, how the planets and everything in our solar system accreted, collided, assembled. Now the question is, does it work everywhere? We have a lot of evidence. We have a lot of evidence for all these thousands of planets that we've discovered. And the answer is, does that evidence also support this theory? Or is there a better theory that would have even more evidence to support it? We'll see if we can't figure that out over the rest of the semester. So, all right. So keep this in mind, right? Keep this theory in mind for when we're talking about these alien worlds, and see if they make sense, right? See if these planets, see if the new planets that we're discovering make sense. Are they also explained by the solar nebula theory? Because that is one of the big burning research questions that we have right now. So, okay. Hopefully this is making sense. If this is making sense, then go ahead, tackle the practice, and on to the next cool thing. See you there, everyone.